Welcome everybody. I get confused a lot on my day-to-day work. It passes usually. But I usually meet code, and I want to understand the intention behind it. That's like what I do. So as a programmer, it's up to us to understand and to decide whether the code we have does what we want it to do, what it should have done. So one day, I'm reading through code, probably fixing warnings, checking warnings, fixing the build system, something, tightening warning flags. That's my favorite. And I met with this code in C++, private, volatile, bool enabled. Like, okay. This was in a class. It was a variable to set the state of running of a thread. And I'm like, this smells like Java. This doesn't smell like C++. Back in my mind, I have the adage of concurrency and volatile in C++ is a no. So the context for us, what we are currently about 100% C++ code base, but we used to have a significant chunk of Java code base. So, and this code was written when we had some Java and some C++. And I'm like, this is probably someone who confuses things. So I'm like, let's fix this. We make it an atomic bool enabled instead. Like, okay, so now we've changed the code. So hopefully we haven't broken anything, and we haven't, because this is strictly, it guarantees quite a lot more. Because in volatile, it just says you have to read it and you have to write it, but you have no guarantees about thread safety or memory and stuff. So this would make it a thread safe, and whether this is a good design for active objects, completely different. But then now I have to explain my fix to the rest of the team. Like, oh my god. So this is stricter behavior. So, and trying to explain it to some of my engineers, I figured out, like, oh no, I don't have the words to describe why it was wrong. So this is why this talk happened. So it feels very trivial to explain this word, but then here we are. So about me, quickly, my name is Inge Fredriksen. I've been programming roughly for 15 years, give or take. Mostly embedded, mostly C++, but also in C#, Java, Python. I've been paid to program in, and also Ada, so that's fine. Graduated from Norwegian University of Science and Technology with a master's civilingeniør in engineering cybernetics. Yeah, about 15 years ago. So yeah, currently working at Tom Recollection. We make reverse vending machines, and yeah, we are hiring, and come talk to us. But then again, yeah, okay. Guarantees. My mind works best with guarantees. So I'm thinking all the time, what does this statement make sense? What does this statement mean? Is it correct? Does the code do what the programmer intended? This is very often the difficult one. The statement can be programmatically legal according to the language, but still wrong for us. So I try to use guarantees to draw the box and figure out where I'm working in. And one way I use it is guarantees, for me, sets the limits for compiler optimizations. Because you say, the language guarantees this and this and this, and the rest, optimizations. Some way of think about it. So, volatile. It's just a word, but it appears in many programming languages. So we'll start by going through some of the languages, the most important ones, I think. And a small heads up, C and C++ will come at the end, because something. So in Java was the thing we started with. And in Java, volatile is a keyword on a class field. And the guarantees for that class field is that this field will be atomic and it will be thread safe to access. For foreshadowing for later, this is not used for memory mapped I/O. Memory mapped I/O in Java is probably behind some library or something. So a typical way in Java to use this is to have some kind of volatile flag. And you can have a thread that just spins on that thread, waits for it to be true, and then print it out. And then you have in the main, we set the number we want to print before we set the ready flag. So because ready is volatile, this while loop will always read a correct value, because if we didn't have volatile on it, it could decide to print 0 instead because of race conditions. So by volatile, we make it atomic, we make it thread safe, everything's good. Easy to talk about. C#, exact same thing. Some say C# is Java 2, but whatever. So it is, you can use it as a keyword on a class field, like in Java, but it also, and then it has the same guarantees. It is atomic and it's thread safe, but in addition, C# adds some standalone functions. One function is to read from a location, and one to write from a location. The guarantees for those is slightly different from the field, in that the calls are never removed. They will always be there, and the runtime or the compiler will say, we will add a memory barrier so that, if, to quote from the standard, from the spec, if a read or write appears after this method in the code, the processor cannot move it before this method. So it guarantees if you see in the code you have a volatile read, nothing can be placed, nothing can be optimized to run before it. So, okay, that's good, because you now have some extra guarantees for the access. And the fact that it uses a memory barrier means that we can use these volatile read and writes to implement things like locks for threads. A different language, D language, largely considered a successor to C++, which supposedly have learned the C++ lessons. It has two library functions, one to do a volatile load and one to do a volatile store. It's only implemented for some few basic types, like unsigned 8-bit, 16-bit, 32, and 64-bit. But it has even fewer guarantees. It doesn't guarantee atomicity, it doesn't guarantee a memory barrier. Everything that it guarantees is that it's never removed. It will always be there in the compiled code. And if you do volatile operations, call these functions, they are never reordered against themselves. So if you have a volatile load and then a volatile store, they cannot be reordered. So it's even weaker. So if you needed to have some extra guarantees, you would probably have to add a memory barrier yourself. So it's even weaker, but it's starting to look like a tiny Lego brick. And you have a memory barrier as another Lego brick, and then you start to build higher abstractions. Go further to Rust. It also has separate functions for this. It takes a pointer, and then you can either read volatile from it, or you can write volatile. These are limited to row pointers and in a same scope. And these have the same guarantees as an IND. It's explicitly non-atomic, and it doesn't have a memory barrier. And to quote from the statistics, it's kind of funny because they just punt to Clang. It basically says, our semantics is basically what C has. So that's kind of fun. I'll take sig for fun. It actually has volatiles on the keyboard, but it limits it to pointers. It has the same guarantees as the ones from the Rust and yeah, and the calls are never removed, and they are never reordered with other volatile accesses. But looking at the docs is always fun because you get some nice quotes. Is if you see code that is using volatile for something other than memory mapped input and output, it's probably a bug. And that's kind of a lesson you should take to C and C++ as well. There are very few uses for volatile. So it's very limited, very good. Want links? There are links. Now C and C++. I'm guessing that's the major reason people are here. All the languages we've seen before have come after C and C++, so they've learned their lessons. In C, volatile is a type qualifier. So you have a type, for example, int, and you can qualify that by being a volatile int. So that's kind of makes sense. And then, but you can add it to pointers as well. And then you started to get some kind of nice explosions. You have A is a pointer to an int, but B is a volatile pointer to an int. C is a pointer to a volatile int. D is a volatile pointer to a volatile int. And I'm confusing myself probably, but yeah. In C, these probably, I hope they don't work, but according to the language, they are legal. But what the... and the fun one at the bottom, for those who can see it, is a member function pointer. A volatile qualified member function pointer. Oh, it doesn't make sense. But let's figure out what why we've come to this. So a quick history of C's relationship with volatile. Because you have some code in your C, some C code, and they reached a problem where the compiler started to optimize things, and suddenly their accesses to CPU registers were gone. Or more specifically, they had a keyboard, and then they tried to read the is there a keyboard interrupt? And then the compiler said, hey, you're only reading from this. I can read it once and just reuse that. So then C said, okay, this is a problem. We have to guarantee that the read occurs every time it seems to occur in the code. So they add the volatile as a fix for this. That's perfectly fine. And then C++ comes along and says, volatile is allowed wherever const is allowed. And things get weird. Because volatile, you can, in C, you can place it everywhere you can place const. And then comes C++ 20, and they have figured out that a lot of these uses of the keyword volatile doesn't really make sense. There are oddities, such as a function parameter that's qualified as volatile. Makes no sense, because you take a variable, you take an argument, and you're guaranteeing to read from it every time. Like, why would you do that? Because if you are, the language is complete control, and if you read it once, it doesn't have an effect. So C++ decides to deprecate a whole lot of stuff, and then backpedals on a few things, because MCU people say, hey, we use this. So that one's back, and then C23 comes along soon and deprecates the same as C++. There are some standards, which is, yeah, it's standards, it's not fun. So welcome to the abstract machine. You have the phrasing an access to an object through the use of an L value of volatile qualified type is a volatile access. Like, it's too much for me. The phrase evaluated strictly according to the rules of the abstract machine means every read must happen because it's considered a side effect, and every write must happen because it's considered a side effect. And the small pointer plus equals is slightly weird because it's, according to the language, is a read, modify, write, but you probably have an increment instructions on your assembly. So an L value of a volatile qualified type I see as basically a phrasing issue to handle casting. So if you have an X, which is a volatile int, and you write 3, the language now guarantees that X is written as 3. Like, okay. But if you had a loop, for example, and you kept assigning 3 to X, then the compiler is obligated to perform the write every single time. And if you have a normal unqualified int, you can take a reference to it, cast that pointer to a volatile qualified int pointer, dereference that, and assign it to 3, and you get the same behavior. Because you have a pointer that says, I'm pointing to something that is volatile, and I'm writing to that as if it was a volatile. Marked as volatile. So that one also happens every single time. So that the phrasing L value of a volatile qualified type is like, okay, non-standard is. We guaranteed that every write happens exactly once for every statement in the code. We guarantee that if it's a write, it happens exactly once. So you have and also you have a guaranteed ordering between those volatile accesses. But importantly, you are not guaranteed ordering related to other non-qualified variables. So if you have a bunch of variables and you try to guard them behind the volatile, that will not work in practice, hopefully. Because compilers are smart and stupid. So that's what I alluded to earlier, because if you have to guarantee accesses to other things, you have to insert memory barriers to ensure that you propagate everything into the memory and things can't move past that one. In practice, volatile is used to catch that things happened outside your program. And program essentially means whatever what the language itself handles. The curious cases are things like CPU registers. Like you can have weird CPU registers that have like write only semantics. Like you cannot read from them. You have registers that have clear on read. Like if you perform a read, the next read will be different. Like you cannot capture that in the C and C++ programming language currently. You probably won't. So the explicit act of performing a read or a write on the hardware is the effect you're wanting to keep. That's the interesting part. It's not manipulating conceptual data in your program. It's performing the actual access towards memory or to CPU registers. So yeah. You use volatile in order to guarantee that the read happens and guarantee that it happens on actual physical read-write hardware. Right? So it's very limited. It's not useful very much. But when you need it, you absolutely need it. So that's why. CPU registered other types of memory mapped I/O typically. And again, it's not just that you read and write data, it's the act that you perform the read and the act that you perform the write. That is the important thing. So you can have some very weird pitfalls It's, for example, the accesses are allowed to tear. So if you say you want to read a 64-bit value on a 32-bit machine, the language is perfectly allowed to compile that as 2 read instructions. So you have to inspect your generated code to ensure that when you do these kind of volatile operations, you get the actual instructions you want. A warning about C-star casts. C-star casts are very liberal in what they do, and it's too easy to cast away volatile. So if you wanted to guarantee that you keep using the volatile semantics for these kind of variables, be very careful with using C-cast, because suddenly you've removed them. And you have to do this explicitly if you have to use memcopy and memset, for example. Memcopy and memset will not work with volatile data. It cannot work because the signature of it is it takes a void pointer. And so if you have something that's volatile, a pointer to volatile int, or conceptually a pointer to volatile void, then you have to cast away the volatile qualifier. And if you access data that is considered was defined as volatile as non-volatile, then you're in undefined behavior territory. And once you hit memset and memcopy, then the compiler can start to use data flow analysis and just remove everything. So yeah. And if you have assignment through assignment, things get kind of weird when you try to figure out which accesses should be kept if one of these is volatile. So just don't. If you use plus equals, if x was volatile qualified, and you would expect it to be an increment instruction on your CPU, but according to the language, it probably should be read followed by an update in memory, and then followed by a write. And that may not be what you do, so that one has been deprecated. The bottom one is I take x and or equals a value, basically a set a bit. And that one is kind of fuzzy right now, because what you would expect from a volatile is that you read the value of x, you set the bit in that value, and you write it back. But some MCU providers, they have said now that we have to have this one back because we generate an increment instruction for this, which technically is not standards compliant, but what can you do? You have another funny thing. What about a volatile union? Can the union active member change from each read? And then I'm confused again. If you want anything, there's too much. So yeah, some comparison for what we have. So the first one, Java and C++, that's when it's used for, hey, I know this is a thread safe thing. This is a thread communication primitive. And then you have the C# function, volatile read and write. Those are more for doing what is in C and C++ and Rust and everything considered a volatile access. But it also inserts a memory barrier, and all the rest one are like, hey, only thing we guarantee is that the read happens and the write happens. So in my brief on this, I promise some helpers and guidelines, but the basic guideline is use it very sparingly. So, but guidelines are for avoiding sharp edges in the language. So if you have several languages that you use in practice, side by side, things can get hairy. And if you once you have a keyword like this that appears with different semantics in different languages, you really should have some proper guidelines in your to help the developers use the right thing. So of the ones we looked at, the only one that really needs helpers is C and C++. And in C, you can only really do macros. So let's do C++ instead. I propose that you add 2 standalone functions to mimic those we saw in D and Rust. That is volatile load and volatile store. These take the pointer that you're working on and the value. So the main benefits of this is you have now given it a name. Just like Kate said earlier this morning, this is a name. This is now an abstraction for you. So now you don't have to check the declaration of the variable or anything. You see that, oh, at this point in a code, I'm performing a volatile store. At this point, I want this exact read to happen every single time. And then you can choose when and when you don't want it. Exactly these kind of templates has been proposed for this ISO C++, but it's requested further revisions for them. Yeah, I tried to implement this one in C when generics and didn't really make it work. So we'll see. The implementation for this, pretty straightforward, but there is quite a lot of noise to make it production ready. Basic function is, it is a template. Don't be afraid. It's a volatile load. It takes the pointer to where it's supposed to load from. Then it casts that one to an L value, whatever, long phrasing. Because you say, I want to cast this pointer to something that points to a volatile instead, dereference it and return it. The implementation is like it's one line. So why does this help? Yeah. Same for store. It takes the destination, it takes the value to point it, just perform whatever you would use normally in C or in C++. Okay. But the uses of these are exactly that they are given an explicit name at the call site. So now the intention is that it's done different from a normal dereferencing operation. Because a normal dereferencing operation, if you have a normal pointer, you say like, I'm just going to read it. But if you have a volatile load, you say that you're using something slightly different. It has an extra effect and not just reading from memory. So by like giving it a different name, you say that things are a bit different here, be careful. Pretty straight stuff. Yeah, we can take this one step further and use a new type instead. The standards have this concept that they call volatile as a device register. And the intention is that if you have volatile, it acts like some kind of weird CPU register. And then we can call this in Embedded, we could, instead of pointer to volatile, we could probably call this register. Like I have a register, I can read from it and I can write to it. What's fun about this one is that I take an access type, marker type, and this means I can actually implement a write only pointer, which is kind of interesting. Sometimes you want to communicate to others that, hey, I'm taking something, I will never read it, I don't want to know how to read it, it is a write only. And a write only pointer is, yeah, fine. There are some template magic in here just to make it basically const correct. So main benefits of this is that it's not what it does, it's all the thing it doesn't do. It doesn't do type conversion, implicit conversions. It doesn't have pointer arithmetic. It can't be used to compound assignments and stuff. So it's very often when you create a new type is to restrict what happens, not enable new stuff. The uses for this is like, it's a comparison between the standalone functions and the object. And now it comes down to what do you prefer in your code. It's always a toss-up whether you want to use standalone functions or you want to use some types. And Jonathan Miller had an article in Accu 170 recently about just this topic, about when to choose a function and when to use a new type. Wrappers are cool and they are very useful. It is an abstraction, but you can always have more, and you probably should. Because Volatile is kind of this weird edge to the language, you always want to compartmentalize and isolate that kind of logic. And names are always good. Thank you, Kate. So a very common one is a register, very useful for embedded. Like I have a register that is my clock, and then it's read only. And whenever I read it, I get the new counter. You could also have, if you have memory mapped I/O talking to an FPGA, you could also have a new type for, like, this is an FPGA bank. And or if you have other shared memory, you can have, I have a shared memory of size, and then you could have functions that have, I want the normal pointer read, or you want the volatile read. Use these kind of helpers for isolating these kind of volatile weirdness, oddities. So yeah, it all depends on your domain, of course. The helpers is not enough. You probably need to tell your colleagues how to use the language, and the guidelines for how, when and when not to use this volatile thingy. So yeah, memory mapped I/O, the only time you really should use volatile. If you don't have memory mapped I/O, or you don't know what it is, you don't need volatile. Basically, that's it. This is a kind of, I know it when I see it kind of thing. I need this kind of extra information, extra guaranteed for every read or write. So yeah, memory mapped I/O, the only time you should use volatile. Use these helpers to perform the read or write, because if you just do a normal read or write, it's very confusable. You don't know when you read the code whether this is a volatile read or it's a normal pointer read. And when that is important, the difference with whether it's a volatile or not, that's when you use helpers, that's when you use a different abstraction, a different name. For example, I want to store into pointer 24601. Okay, this means, okay, I have this pointer and I explicitly want to write that value, because by writing that value, probably I'm triggering some interrupt in an FPGA or something. You could also, as I said, you could have a register that is uint32. It is a read only, and that's my counter, my clock in embedded. And then you could have the FPGA bank number 42. Like, okay, I'm working on this kind of chunk. And should probably note that memory mapped I/O is a general term. This particularly includes like CPU registers. It's like one of the most common memory mapped I/O, at least for embedded. And another thing is threading. Don't use volatile. Use atomics. Use locks, because those give you guarantees for execution order for everything else. And the standard library in C++ have all the things you want. So check C++ reference for that. And I've been telling a small lie, because you might have to use volatile when talking to a signal handler. In earlier versions of C, volatile sig atomic T was the only allowed way to talk from a signal handler to the rest of your program. It was the only thing that was blessed. Now you probably use other normal atomic types. So yeah, if you see volatile sig atomic, or even worse, if you see sig atomic which is not volatile qualified, then you should write a patch immediately, probably, because then your signal handler don't work. Signal handlers are a weird beast in its own. You basically only have to, you're allowed to set the value and then return. That's everything you basically can do. So yeah, some actual phrasings that I hope you can use is, let's say, only use volatile for memory mapped I/O. Like, that's the kind of sentence I would like to see in a coding guideline. Or use the provided helpers when accessing memory mapped I/O. Again, go back to Kate Gregory's. It is a new name. It is a different thing from normal read or write. Another thing, use locks or atomics when synchronizing threads. Like, straight to the point, direct action, use this. Use atomic to communicate from signal handlers. And the last one is always use C++ style typecast. This one probably covers many other things, but then you cannot accidentally cast away volatile, which would probably land you right in undefined behavior. So yeah, GCC can give you all these errors. Yeah, universally helpful. I hope some of these are useful. To me, volatile as a keyword was, and probably still is, kind of confusable. I think that C and C++ currently allow it in way too many places. Like, if you have a variable x that you declare as volatile, like, it doesn't, if I write to this, it doesn't have an association to the outside world, so why does it matter that the actual read happens every single time? So yeah, this is kind of why the newer languages only take volatile through pointers. Like, the normal case is you have a pointer to some part of memory mapped, device register exact address or something, and you do the write through that pointer, and every time. So that's, if you see a standalone variable that's marked as volatile, I would ask the author of why that happens. So yeah, I really think you should have helper wrappers available. Really, really do. So, and to complement that, you have to have guidelines to say, use this. And guidelines, I've read a lot of guidelines, and they are very often like suggestive and do this, prefer that. Like, try to have it as direct as possible. Like, use this, don't use this, use it. So I'm blazing ahead, so I'm sorry, but thank you. So we are way ahead of schedule. I was quite nervous. So, any questions? Yes. Not guaranteed. It's not guaranteed because Microsoft didn't catch up. If you have, the question was if you have volatile qualified fields of a struct, right? And you use that one to communicate to some other component to start and stop a thread. That's the exact problem with it, is because you don't have a memory barrier, so that flag cannot guard anything. So if your thread accesses any other data, it can still access that data even though you've toggled the flag. So you get this kind of, yeah, you toggle the flag, but I'm choosing to ignore it because I moved code around the check. And this is why you have to have these kind of memory barriers to explicitly say everything below, everything above this has to have happened before I continue. So the combination of a memory barrier and then a volatile read could get you somewhere. But again, I just say use an atomic instead. It's a perfectly implemented piece of code. It's in the standard library. It always guarantees what you want. And you don't have to try to communicate to the other ones why this kind of trickery or things will actually do what you want. It's just, it's easier to explain to others. But to further elaborate, it might work in single thread. Any other? So yeah, please contact me if anything. Say hello to me personally. The font has been Atkinson Hyperlegible from Braille Institute. It's great. And if you want, you can join me at work, complain to me, make me change my mind, do whatever. Thank you.